We have already completed the first unit of waves and oscillation, and from today we are going to see the discussions on its second unit. Actually, in second unit we are going to see the theories related to the superposition of simple harmonic oscillations. Actually, in first chapter you have seen that we have discussed only the simple harmonic motion of systems having 1 degree of freedom. Okay, but there are several situations which we will come across in in our forthcoming chapters, which actually involve the simultaneous application, or you can say the superposition of 2 or more simple harmonic oscillations on the same system. Actually, such situations are particularly common in acoustics. In our forthcoming video, we will also see the chapter on acoustics. Okay. For example, when you talk about a microphone diaphragm or a human eardrum, these are actually subjected simultaneously to various vibrations, and the actual motion or the of the diaphragm or the eardrum correspond to the resultant effect of the superposition of various vibrations. Okay. So in this chapter we will see the basic principle of this superposition principle. Since it is our first video on this superposition of harmonic oscillations, so this is just an introductory video. And in this introduction, we will learn about a very important basic fundamental that we cannot actually superpose, or we cannot always get this superposition principle is not always valid. But when it will be valid, when it is invalid, such conditions will be discussed in this first video. So it is a very useful concept, and after that we will see the basic theory of this chapter and its applications. Okay. So actually, in order to obtain the resultant of 2 or more harmonic oscillations, we shall make use of a very important principle that is called superposition principle. This superposition principle is a well-known principle of physics, and its use is in different branches of physics. Okay? Even in classical mechanics, in Newtonian mechanics, you use the principle of superposition. In quantum mechanics, you use the principle of superposition. In atomic and molecular physics, we also use the superposition principle. Okay? So this is a very important and very basic and fundamental principle. So actually, what is this superposition principle, and when it will be applicable? In fact, we will see that this superposition principle does not hold always, but there is a particular family of linear differential equation which is called homogeneous linear differential equation. Only then this principle will be applicable, but in case of non-linear differential equation, this principle is not valid. This cannot be applied. So basically, if you talk about the superposition principle in one sentence, what is this superposition principle? You can say that this superposition principle states that the resultant of 2 or more harmonic displacements is simply the algebraic sum of the individual displacement. So if you consider that x1 and x2 are 2 simple harmonic displacements, okay, these are displacement of a linear harmonic oscillator, then according to this principle, when the oscillator will experience both the oscillations simultaneously, both the vibrations simultaneously. If you consider that this is your oscillator, and you impose a restoring force F1, and under this F1 this oscillates, and at any moment of time t its displacement is x1. Now you consider that this harmonic oscillator is subjected to another restoring force, let us say F2, and under this, when it oscillates, at any moment its displacement is x2. Then what will happen when both of these restoring force will act on this system simultaneously? If F1 plus F2 will be applied on the oscillator, then what will be its displacement at any time t? According to superposition principle, this x will be simply the algebraic sum, or you can say the vector sum of this x1 and x2. Okay? This is actually the superposition principle in its basic form. Okay? But as I have told you that this superposition principle in context of harmonic oscillation may be valid or may be invalid. It may be applicable or it may not be applicable. So first of all, before going through the proper theory of this chapter, first of all we are going to learn in this introduction that when this superposition principle can be applied. Okay? Actually, as I have told you that we have discussed in detail the oscillations of system with 1 degree of freedom, in which the moving part always stays close to the equilibrium position. When you have studied simple harmonic motion, then you have seen that an oscillatory motion is simple harmonic only when the oscillator actually oscillates in the region near about the equilibrium position O. This is called a small oscillation. And actually in that condition, the force or the restoring force acting on the oscillator is directly proportional to its displacement and oppositely directed. But this happens only in case of a small oscillation. When you take the oscillation near about the equilibrium position, only then such relation is valid. So you can say that in case of a small oscillation with 1 degree of freedom, this restoring force F is proportional to the displacement x, and it always tends to decrease x. F always tends to decrease x. Okay? It means the force has a tendency to bring the oscillator at the position of the equilibrium position or at the mean position. Okay? So F in this case, where F is restoring force, that is given as minus kx. You know it. You have already studied these things. Okay? Where k is called a force constant. Okay? Now, according to Newton's second law of motion, F is equal to mass times acceleration of the particle or the system or the oscillator. Since x is its displacement at any moment t, so d2x by dt square, this is actually the acceleration of the oscillator. Okay? So according to Newton's second law of motion, F will be given by m times d2x by dt square. And therefore, you can write the equation of motion, this harmonic oscillator, in this form, that m times d2x by dt square is equal to minus kx. And therefore, you can write that d2x by dt square is equal to minus k over m times x. And when you will bring this term k over m times x in LHS, this will become plus. So the equation of motion is this: d2x by dt square plus k over mx equal to 0. In fact, this k over m is replaced by omega square. Already you have discussed these things earlier. Okay, I am just repeating the things. And this omega, which is a square root of k over m, this is actually called the cyclic frequency or the angular frequency of this harmonic oscillation. Okay, and this second order differential equation with constant coefficient defined in equation 2, this is actually the differential equation of the simple harmonic motion, okay, or the differential equation of the harmonic oscillator. Okay, so you can see that actually this equation 2, if you will observe this equation 2 seriously, you can see that in this equation actually there are two terms contained here, two variables, that is x and d2x by dt square. X is an independent variable and d2x by dt square is acceleration, which will be also variable. Okay. So the equation of motion of simple harmonic motion contains terms that depend on x and d2x by dt square. Okay, and there is no other term in this equation which will depend on the higher power of x or d2x by dt square. It means in this differential equation, both of the terms d2x by dt square and x contain power 1, not 2, not 3. You know, you have actually in your first semester examination, you have studied the course on differential equation, both in physics and mathematics. And you know, such a differential equation in which no term containing a higher power on x or d2x by dt square is present, that is called a linear equation. So this differential equation 2, which is actually the equation of motion of simple harmonic motion, this is a second order differential equation which is linear. Okay, so this is a linear differential equation. Okay, so you can say that a linear differential equation is one that contains terms that depend only on the first powers of the variable and its derivative. Okay, that such an equation is called a linear equation. Okay. Now, on the other hand, if the moving part of the system oscillates violently, okay, that is with large amplitude, then what will happen? Actually, in that case, when there is a violent oscillation or oscillation with large amplitude, the moving part does not remain near about the equilibrium position. Actually, during its oscillation, it moves far and far away from the equilibrium position, and in that condition, actually, you can say that there will be the oscillation with large amplitude. For example, in the case of simple pendulum, you have seen that when sin theta cannot be replaced by theta. We have discussed already the problem of simple pendulum, and you consider that this theta is the angular displacement at any time t. Okay. Then, in case of a small oscillation of this simple pendulum, you consider theta very small, almost equal to 2 degree, 3 degree, 1 degree or 4 degree. And in that condition, you take sin theta equal to theta. But if let us consider theta equal to 60 degree, it is 80 degree. Can you take sin theta equal to theta? Answer is no. Actually, in that condition, the restoring force does not contain only x, but the expression for this restoring force will contain higher powers of x2, the terms on which x will contain higher power, such terms will be also contained. Okay. So I have written here, you can see that with large amplitude, the restoring force would contain terms that depend on x, x square, x cube, x4 and so on. Okay. In other words, you can say that the restoring force would not be linear in x. So when oscillation is not of a small amplitude, but it is of larger amplitude, violent oscillation, in that condition, the restoring force is not a linear function of x, or you can say that f equal to minus kx, this is just an equation of a straight line. So we simply say that in this case, the restoring force varies linearly with x. But in case of oscillation with large amplitude, this linear nature of restoring force will not remain. But this f will vary non-linearly with x. Okay, it may depend on x square, x cube, x4, and so on. Okay, and actually in that condition, the equation of motion will be also not of this form as you have seen in this equation 2. But the equation of motion will also contain the term like x square, x cube, x4, and so on. And so the equation of motion then become non-linear, not linear. So in nutshell, you can say when we talk about the a simple harmonic motion with 1 degree of freedom with a small amplitude, or we consider only a small oscillation, then the restoring force is linear. It is a linear function of displacement x. The equation of motion is also a linear differential equation. But when we consider the violent oscillation, that is oscillation with larger amplitude, in that condition, the restoring force is not a linear function of x, but it will be a non-linear function of x. And the equation of motion of such an oscillation at the same time will be also a non-linear differential equation. Okay? Actually, in your course on differential equation, you have also learned about the homogeneous equation. A homogeneous equation actually contains no terms independent of the variable x. It means in a homogeneous differential equation, that all terms will be only a function of x. Okay, so you can say that linear homogeneous differential equations have a very interesting and important property. And what is that property? That property is the sum of any two solutions is itself a solution, which is also the statement of principle of superposition. Actually, when you will take the second order differential equation, okay, it can have two independent solutions, okay, or more independent solution in accordance with the initial condition. For different initial condition, a differential equation has different solutions. Okay, so if you consider two solutions of the homogeneous linear differential equation, then when you will actually sum up the two solutions, the sum of the two independent solution of the differential equation, homogeneous linear differential equation, will be also a solution of that very equation. And this is actually the principle of superposition. This is also the statement of the superposition principle. Okay. So you can say that the superposition principle holds only for linear differential equations. This is the most important fact, that the superposition principle holds only for linear differential equations. Okay? It does not apply if the equations are non-linear. Okay? In other words, you can say that the sum of two solutions of a non-linear differential equation is not itself the solution of that very equation. The sum of the two independent solutions of a linear differential equation, mark it. that sum will be also the solution of that linear differential equation. But if you consider the two independent solution of a non-linear differential equation and you add those two solutions, that sum of two independent solution of a non-linear differential equation is not the solution of the equation itself. Okay? So it is a very remarkable fact that if this equation, which is a linear differential equation, equation number 2, has two solutions, let us say x1 and x2, okay? Then x1 plus x2 will be also a solution of this equation 2. But if you will consider a non-linear differential equation and that non-linear differential equation has two solutions, let us say x1, x2, then x1 plus x2 is not a solution of that non-linear differential equation. This is a very remarkable fact. I have stated this fact directly here, but now we are going to see the proof of this statement. Okay? So now we shall prove the statement by considering a particularly simple non-differential equation. We will consider a simple non-differential equation and then we will prove that the sum of the two or more independent solutions of a non-linear differential equation cannot be the solution of that very equation. Now, by analytical method, by calculation, we can prove it. Okay? And for proving this fact, let us consider the oscillation of a system with 1 degree of freedom. And let us say that the motion of that system is governed by the equation of this form. d2x by dt square is equal to minus omega square x plus alpha x square plus beta x cube plus so on. You know, if these two terms, alpha x square, beta x cube and other higher terms are not present, your equation is only d2x by dt square equal to minus omega square x. Then this is a linear differential equation, you can see. But along with this term minus omega square x, if you consider the terms containing the higher powers of x, then this equation is a non-linear differential equation. Okay? So I have considered here a non-linear differential equation defined in this equation 3. Okay? You can say that this is actually a non-linear differential equation because this equation contains the term like x square, x cube and so on. Okay? But if you see this equation seriously and you can say that this non-linear equation will become a linear differential equation, but only when both of alpha and beta and other terms if present are equal to 0. So if the constants alpha, beta and so on in this equation 3 are all 0, okay, or you can say that can be taken to be 0 as a sufficiently good approximation, then this equation will simply become d2x by dt square equal to minus omega square x. And you know, then this equation will be a linear homogeneous equation. But if alpha, beta and so on are not 0, then this is a non-linear differential equation. Okay? Actually, the solution of this equation 3 is not very easy. You can't solve this equation in an easy manner. Actually, we do not need to solve it either. So, let us suppose that we have somehow solved it. Okay, and when you will solve it, let us consider that this x1 of t and x2 of t are the two independent solutions of this equation defined in 3. Okay, let us consider. Now you know by hypothesis that if x1 and x2 are the solution of equation 3, then definitely x1, x2 will satisfy equation 3, because solution of any differential equation always satisfies the differential equation. So x1, x2 must satisfy equation 3. So when x1 will satisfy equation 3, what you can write? Instead of x, now you should write x1 and equation will get satisfied. So you can write d2x1 by dt square equal to minus omega square x1 plus alpha x1 square plus beta x1 cube and so on. Similarly, as x2 is also the solution of that very equation, so x2 will also satisfy it, and therefore you can write d2x2 by dt square equal to minus omega square x2 plus alpha x2 square plus beta x cube plus so on. Okay. Actually, it is interesting to find out that whether or not the superposition of x1 and x2 defined by the sum x equal to x1 plus x2 satisfies the same equation of motion or not. Okay. So we shall assume that if that it does, and then arrive at a contradiction. You will see if this is x equal to x1 plus x2 is also a solution of this equation 3, then we must have this equation. By replacing the x by x1 plus x2 from equation 3, you can write d2 by dt square operated on x1 plus x2. Instead of x in this equation 3, I have written actually x1 plus x2. Okay, and that will be equal. So x in this equation number 3 will be replaced by x1 plus x2 in accordance with our assumption that x1 plus x2 is also a solution of this equation. We consider it. We will check it later on that our assumption is correct or not. But for a time being, I have assumed that x1 plus x2 is equal to x, and this is also the solution of equation 3. And therefore, now this equation 3 can be written as replacing x by x1 plus x2. And therefore, you can see when x will be replaced by x1 plus x2, then this equation 3 will become like this. This is d2 by dt square operated on x1 plus x2 equal to minus omega square times x1 plus x2 alpha times x1 plus x2 whole square, because here there was x square, plus beta x cube, but now instead of x you will write x1 plus x2. So this is beta times x1 plus x2 whole cube. Okay. Now let us add these two equations 4 and 5. Okay. After adding these two equations, what we will get, let us now see. In LHS, there will be d2x1 by dt square plus d2x2 by dt square. And in RHS, let us see. There will be minus omega square x1 minus omega square x2. Okay. Plus alpha x1 square plus alpha x2 square plus beta x1 cube plus beta x2 cube. Okay. Now, let us see. If our assumption that x equal to x1 plus x2 is also a solution of equation 3, then these two equations 6 and 7 must agree with one another, or you can say these two equations must hold simultaneously. But it is obvious that both of these equations do not hold simultaneously, or because these two will hold simultaneously if and only if these four conditions will get satisfied. Only then you can say that these two equations agree with one another. So the necessary and the sufficient condition that these two equations 6 and 7 will agree with one another are what? These conditions are: this LHS must be equal to the LHS of equation 7. So d2 by dt square operated on x1 plus x2 must be equal to d2 x1 by dt square plus d2 x2 by dt square. Okay. Again, the term minus omega square times x1 plus x2, this must be equal to sum of these first two terms. So the second condition is minus omega square times x1 plus x2 must be equal to minus omega square x1 minus omega square x2. Okay. The third condition which must be satisfied for the agreement of these two equations are what? That is, alpha times x1 plus x2 whole square must be equal to alpha x1 square plus alpha x2 square. This much. Okay. And the fourth condition is beta times x1 plus x2 whole cube must be equal to this much. Okay. But when you will see these conditions, you can see that the first two conditions, that is A1 and A2, are true, or you can say valid. But the last two conditions, that is A2 and A3, are not valid, are not true. Actually, these will be true only when alpha and beta both will vanish, both are zero. Only then you can say that these will be valid. Because you know, in LHS there is x1 plus x2 whole square. Instead of that, in RHS there is only x1 square plus x2 square. But you know, x1 plus x2 whole square will also contain 2x1 x2, which is not present in RHS. So definitely you can say that these two conditions will not hold. Only the first and the second condition, that is A1 and A2, will hold. In other words, you can say that our assumption that x1 plus x2 plus x2 is a solution of that equation 3 which you have seen here. This equation 3 has a solution of x1 plus x2, okay, can be realized if and only if the non-linear terms, that is those with constants alpha and beta etc., are absent. When these terms will be absent, these terms will be absent, only then the condition that x1 plus x2 is also the solution of equation 3 will be valid, will be true. Okay. So in this way we conclude that the superposition of two solutions is itself a solution if and only if the equation is linear. Okay. That is, the superposition principle does not hold for the non-linear differential equation. Okay. So the superposition principle does not hold for the non-linear differential equation, it holds only for the linear differential equation. So I think by this these arguments, now it is very clear to you that this superposition principle can be applied only when our differential equation is a homogeneous linear differential equation. So if the oscillation is governed by the linear differential equation, or its equation of motion is a linear differential equation, then such oscillations can be superposed on the basis of superposition principle. If you talk about the oscillation with larger amplitude whose equations of motions are not linear, then you can't use the superposition principle. And that condition you can say that if x1, x2 are the solution of two non-linear differential equation, then x1 plus x2 cannot be a solution of that non-linear equation. But if x1, x2 are the solution of a linear differential equation, then x1 plus x2 is also one of its solution. Okay. Now I think it is very clear to you. Actually, why we study this superposition principle? Why it is important? What is its importance in physics? In nutshell, you can say that this superposition principle, when is applied, we save ourselves from a lengthy calculation, from a lengthy process. We can easily find the resultant of two or more simple harmonic vibrations by utilizing this superposition principle, okay, for which we have to make no rigorous calculation. Actually, to illustrate or to explain the application or the importance of this superposition principle, let us consider the example of a linear simple harmonic oscillator. For example, you can consider a spring mass system. You can consider the motion of a simple pendulum. Okay, and we have studied very detailed in first unit that for a small oscillation of a linear harmonic oscillator, the equation of motion is given as d2x by dt square plus omega square x equal to 0. This is actually a linear differential equation, Here, omega, is the angular frequency of the oscillator. Okay. Now, actually, when we want to solve this linear differential equation, you have already seen the solution of this equation in the first unit on the discussion on simple harmonic motion. I have provided a series of video in that chapter, and you have seen how we can solve this differential equation. And you can definitely remember that whenever we want to solve this equation, first of all, we have to take a set of initial conditions. When you say initial conditions, that means you must take time t equal to 0. What is that value of displacement x? What is x at t equal to 0? What is v, which is dx by dt at t equal to 0? Okay. So taking a set of values of x and v at t equal to 0, which are called initial conditions, we obtain a particular solution of this differential equation. And you have seen that the solution of this differential equation for a particular given set of initial condition, if we consider that it is x1, then this solution is given as x1 of t equal to a1 times sine of omega t plus phi 1. Instead of sine, you can also write cosine function. So you may write a1 cos omega t plus phi 1. Okay. Actually here, a1 is called the amplitude of the oscillation or the oscillator, and phi 1 is called the initial phase or angle or epoch or phase constant. This is actually phase of the oscillator at t equal to 0. And these a1 and phi 1, you have learnt earlier that these can be determined from the given initial condition. Considering this condition, you determine the value of a1 and phi 1. How we determine it, you have already learnt in my previous video. Okay. here you must remember that the angular frequency omega does not depend upon the initial conditions. Okay. So if you will change the initial condition, it means you are now going to take another set of initial conditions. Let us take another value of x and b at t equal to 0. Actually, in that condition, omega will remain same, but a1 and phi1 will get changed, because a and phi, which are amplitude and the phase constant, that depends on the initial condition. So for another set of initial condition, let us consider that the solution of that equation is x2 of t, and that is given as a2 times sine of omega t plus phi 2. Okay. Again, this a2 and phi 2, can be determined from the new set of initial conditions. Okay. Now suppose we prescribe a third set of initial conditions. And how we prescribe it? We superpose the initial conditions corresponding to x1 and x2. When you say that we will superpose the initial conditions for x1 and x2, that means we give an initial displacement equal to the sum of the initial displacement of previous two cases. Okay? And the initial velocity, which will be actually the sum of the velocities corresponding to x1 and x2. Okay? So I have mentioned in nutshell here that the third set of initial condition, which is just the sum of the previous two initial conditions. When you say the sum of previous two initial conditions, that means we will give an initial displacement which will be equal to the sum of the initial displacement corresponding to x1 and x2. And we will also give the initial velocity, which will be the sum of the initial velocity in case of x1 and x2. Okay? And now let us say that in this condition, the new displacement becomes x3. Okay? Then, according to superposition principle, the new motion described by this x3 is simply given by the superposition of x1 and x2. That is, x3 will be equal to x1 plus x2. Okay? So there is no need to solve the equation of motion to find the new motion. This is the usefulness. This is the importance of superposition principle. You have obtained this x3. For obtaining x3, there is no need to solve that differential equation in independent manner. If you have solved the equation for two values x1 and x2, then when you will superpose these two conditions, it means both the restoring force will be applied on the oscillator simultaneously. Then what will happen? To know that we have no need of finding the solution of equation of motion in independent manner, but we will simply add the initial two solutions to get the solution of that equation of motion in this condition. This is actually the basic importance. This is the utility. This is the importance of superposition principle. Okay? Because without solving the differential equation in independent manner, we can get the solution. Okay? But for this, if this is your oscillator, okay, it was suffering displacement x1 under the restoring force F1. Now it suffers the displacement x2 under the restoring force F2. And when you will apply both of these forces simultaneously, then the displacement x3 will be simply x1 plus x2. Without finding the solution of equation of motion, if you know x1, x2, you can get x3. This is its usefulness. So you can say that the resultant of two or more harmonic displacements is given by the algebraic sum of the individual displacements. Okay? And you should also remember that this result holds only if the equation of motion is linear. Only if the equation of motion is linear, only then it will be valid. Actually, now in our forthcoming lecture, we will apply the principle to deduce the resultant of various kinds of superposition of two or more harmonic displacement. Okay, so I think definitely this introductory lecture on the superposition of harmonic oscillations have been pleasant for you. Okay, so watch the video seriously and now wait for my second video on it. That will be very useful for you. Okay, thank you very much.